In this video, we're going to look at 4 exponential and log equations that require using properties of logs to solve. So let's go ahead and start with this exponential function. And this one, depending on how you want to do it, could use 1 or 2 log rules. One rule that you'll probably want to use is something of the variety e to the negative x equals 1 over e to the x. That's one of our log rules. And if I rewrite this using that property, what I'll get is something like e to the x equals 4 times 1 over e to the x. So there's one of our rules. And now, if I want to solve this, it's a good idea to get all of my e to the x's together and then have my other stuff elsewhere. So let's go ahead and try to move that e to the x so that it's with the other one. I'll do that by multiplying each side by e to the x. And then there's a couple different ways you can do this problem. One way would be to get, we have e to the x squared. So I'll actually split this up into 2 spaces. We have e to the x times e to the x. So we have e to the x squared equals 4. And one thing I could do is I could square root both sides to get e to the x equals plus or minus 2. And then log both sides. I have e to the x. I want to undo this e to the x. So I undo e to the x by doing natural log. So I'd get natural log, sorry, not natural log. On this side, we get natural log of plus or minus 2. Keep in mind that's 2 different numbers. X equals, and then we have just x on the other side. Because we took natural log, that undid this e, so all I'm left with is this x. But keep in mind, I can't log a negative. So I'm only left with the answer, x equals natural log of 2. And that would be my answer. So that's one way to do this. There's another way you could do this that still uses this same start, but instead of writing this as e to the x squared, I'm going to write this as e to the x times e to the x. I have a rule that says that e to the x times e to the y equals e to the x plus y. So that tells me that e to the x times e to the x is going to be e to the 2x equals 4. Then I can take the log of both sides to cancel out this e here. So I'm left with 2x equals natural log of 4. And then I just divide by 2. And I get x equals natural log of 4 over 2. And this is the same answer. If you really wanted to see why, you could use the fact that this is natural log of 2 squared over 2. Which is natural log, or 2 times natural log of 2 over 2. The 2's cancel. It's the natural log of 2. So, but this answer, for my purposes, is just fine. So either of these would be a correct approach to answer that problem. Next, we're going to look at this problem where I have a couple logs separated by subtraction. And the rule we want to start with here is that log of x minus log of y equals log, I'm not going to be able to write there, equals log of x over y. So I can take 2 logs that are being subtracted and turn it into a single log that has division inside. So let's go ahead and use that rule to simplify the left-hand side, because I want to get this all into one big log. Because if I have this all in one big log, I can undo that log by raising each side 2 to the power of each side. So let's get it all in one big log. So we'll change this into log base 2 of 10x over 3 plus x equals 3. And now I have something in a log on one side and I have a number on the other side. So I can get rid of the log and get x outside of the log by just doing 2 to the power of each side. On the right-hand side, that's going to look like 2 to the 3. And on the left-hand side, it's just going to undo this log, and I'm left with 10x over 3 plus x. Now 2 to the 3 equals 8. So now I just have 10x over 3 plus x equals 8, which isn't necessarily easy, but it's also not the hardest thing we've seen. I can go ahead and multiply both sides by 3 plus x. We get 10x equals 24 plus 8x. I can subtract 8x from both sides. We get that 2x equals 24. Last but not least, we divide by 2 to get x equals 12. Now, it's good to check, does that match the equation I started with? Or specifically what I'm asking is, am I allowed to plug in 12 there, or does that break anything if I do? Well, if I plug in 12, I get log base 2 of 120, and I'm looking, is that a positive number? Yes, it is. So that's fine. Then over here, I get log base 2 of 15. That's also a positive number, so that's fine. That's fine too. So this answer does work. I don't get any extra solutions I don't want, and we're done there. So, all right. Let's take a look at our last two problems. Once again, for this problem, I want to start by getting everything inside of one log. But not only do I have some subtraction, I also have this 2 up front of this natural log. So another rule, and actually a rule that comes in handy quite a bit, that I want to use is that y times log of x equals log of x to the y. So we usually use this going from the right to the left. If I have something, log of something raised to a power, I can take that power up front. But here we're going to take something that's multiplied up front and move it inside as an exponent. So that's going to let me rewrite this first term. So I have natural log of x squared minus natural log of 2x equals 2. And now that I have that, I have something in a log minus something in a log. I can now use my rule that we used in the previous problem, that log of x minus log of y equals log of x over y. And that's going to let me get everything in a single log. So I'll rewrite that. We get natural log of x squared over 2x equals 2. And we can actually do a little bit of simplification inside the log. This is just going to be natural log of x over 2 equals 2. And now I have something in a log on one side. I have a number on the other side. I can undo it by raising each side, or by taking each side and putting it in the exponent of some base. But what base am I going to use? Well, remember, natural log is just log base e. So what I do to undo this is I do e to the power of each side. So on the right-hand side, that's going to be e squared. And on the left-hand side, it just undoes this log, and I'm left with x over 2. Last but not least, I have x over 2 equals e squared. I can just multiply both sides by 2, and I'm done getting x equals e squared, or 2e squared. Again, let's check. Does that make any of these negative? No, it does not. We're good. So, last but not least, we have this log of x plus log of x plus 3 equals 1. Again, I want to get everything inside a single log. And instead of using this subtraction rule, I'm going to use the addition rule that I have, which says that log of x plus log of y equals log of x times y. So let's go ahead and rewrite this as log of x times x plus 3 equals 1. And I can do a little bit of foiling inside. Well, it's not even foiling, it's just distributing. I get log of x squared plus 3x equals 1. Now I have everything inside a log on one side, and I have a number on the other side. So let's go ahead and try to cancel that log by doing some number to both sides. And now I have to remember, oh, it doesn't say anything here. If it doesn't say anything, we have log base 10. So let's go ahead and raise 10 to the power of both sides. On this right side, we'll have 10. On the left side, we'll have x squared plus 3x. And now I just have a polynomial that I know how to solve. I'll go ahead and start by getting one side equal to 0. So we'll have x squared plus 3x minus 10 equals 0. I can make a little diamond. I want two numbers that multiply to negative 10 and add to 3. After you think about that a little bit, you'll get that 5 and negative 2 work great. So we get x plus 5 times x minus 2 equals 0. And we get x equals negative 5, x equals 2 as our solutions. But, there's a big but here, x equals 2, that's fine. When I plug that into these, I get 2 log of 2 and log of 5. Great. If I plug in x equals negative 5 to my original equation, I get log of negative 5 and log of negative 2. Since I can't take a log of a negative number, that solution doesn't work because I can't log a negative. So there we go. We only actually have one solution there, x equals 2. So there's some more examples of how to solve equations using properties of logarithms. And hopefully that helps a little bit.